Welcome back to the Warnell Seminar. We've only got one more in the series coming up. So next weekend's going to be our last Warnell seminar, and then those in the class will have some kind of like follow up, one more meet. Just make sure y'all pass this around maybe and sign in. Today's speaker is our own Dr. Clark Rushing. I'm gonna take Dr. Rushing for granted, dude. I didn't even think of like coming up with some kind of like great biography to introduce Dr. Rushing, but ornithologist by trade, right? And we're excited to have him. So take it away, Clark.
Oh, that's it?
Yeah.
Okay, yeah, thanks. This is fun. A lot of familiar faces, including a lot of like experimental design people, and it's weird. It's like Thursday and you guys are sitting in different places. But you normally sit in this room, except for you.
These are our seats.
Yeah, okay, great. Okay, thanks. So I'm gonna start off by just sort of being honest that when Bynum emailed me several months ago and said that I guess there's some kind of vote.
Yeah, we had like a poll of who we wanted to speak.
Still haven't seen the result myself. Trying to decide what to give a talk about, and had some stuff that I had been talking about that I had given a few talks on and was a little bit bored with, and a hard point in the semester to put something new together, and so I was kind of struggling a little bit, and I thought about the time Bynum asked, I had just gotten my tenure letter, and I was like, oh, this is great, I can talk about whatever I want now. And so I was trying to think through, like, okay, what can I put together like a 45-minute presentation on, and it's not going to be, an incredible amount of work. Some people that know me know I have very strong and complicated feelings about Jimmy Buffett. More than prepared to talk for 45 minutes about his rightful place in American music.
Prove it.
I thought, okay, no, that's not the time and place for this. I have very strong feelings on the International Olympic Committee removing lightweight rowing and replacing it with whatever coastal rowing is. Could also speak for 45 minutes about that. If anybody wants to hear those talks, just follow up with me afterwards. I'm more than happy to hear them. So then I thought, okay, we've been doing some fun stuff with these self-exciting point process models, and I know that people in this room, you all probably have very strong feelings about self-exciting point process models, so that would probably be a little redundant with stuff everybody's already thinking about, so probably not a good talk either. And so I ended up sort of thinking about some projects that I currently have going on, none of which were really quite at a point where I thought they were a full 45-minute seminar, but sort of thinking through some common threads of those talks that could, or those projects that could form the basis of a talk. And the thread that I decided to sort of follow, and I'll admit that, we'll see, these are a little bit half-baked in my brain, but hopefully it'll be okay, is in our lab, at least, we're at this point where we're using a lot of kind of new and emerging technologies. And both in our own work and talking to colleagues and going to conferences, realizing that these new data are both a huge opportunity, but also a challenge, and a challenge that often comes down to using statistical methods that sort of match the complexities of these new data sets. So I'm going to sort of structure a talk around that idea. If you're in this room, you're probably familiar with some type of new technology, right? There's been a rapid increase in technological tools in wildlife ecology and other disciplines that are really opening the door to all sorts of new questions, answering old questions that previously we couldn't answer. Camera traps, ARU recorders, RFID and pit tagging, acoustic telemetry, automated telemetry. These are all experiencing really rapid growth And there's been a lot of excitement and a lot of data. If you've gone to any conference recently, you've probably been in a symposium or seen dozens of talks on these different technologies. At the same time, there's been, really rapid growth in statistical methods that are being used in wildlife ecology and related disciplines. So you probably, even if you're a student, you probably, also encountered, more sophisticated statistical methods, more complicated methods. And so, it's pretty common now to like go to a talk or open a paper and see something, kind of like this. And I promise I'm going to keep this talk very conceptual, very little actual math in this talk. And I know you all probably saw this and realized, obviously, this is a model to estimate duration and phenology of feather molt in birds. So this is quite common, right? And at the same time that we're seeing models with this level of complexity, there's this kind of dynamic that has gone along with that growth, which I think is some kind of tension between the people who lean into models like this and the people who are sort of like, wait a second, all we're trying to do is figure out when a bird is growing its feathers. Why are you making me do all of this? And I think some of those people look at this, a model like this, and think that the person who did this is just, it's like kind of statistical navel gazing, right? It's like we just do it because we can, because we like the math. And that's actually resulted in, some actual pushback. And this is a little bit outdated. I think this was maybe a decade ago or so, or 2017, so almost a decade ago. There were these blog posts where they coined this term statistical machismo. And it was this idea that like all of these complicated models are just being used by people who are either trying to show off or they're trying to sort of gatekeep during the publication process and like have a way to reject papers because it didn't use some fancy new model. And like this kind of took off, like this became its own kind of thing. And if you have a few hours to spare, I highly recommend not the blog posts so much themselves, but the comment section. You're gonna need like 2 or 3 hours, I promise you. And it's like a who's who of statistical ecology trying to explain the finer points of some of these issues as best they can, as well as like reality show drama with like name calling and all sorts. I mean, it's really crazy. I tried to like sort of sum it up. If you don't want to read the whole comment section, some basically it comes down to people saying, the systems we're trying to learn about and the data we're collecting are complicated. And you can't just ignore those complexities. Versus other people who are saying, no, simple models are fine, and this is just showing off and gatekeeping. You probably can guess kind of where I would stand on this issue. And kind of the rest of this talk, what I'm going to try to do is using a few examples, make the case that we do deal with complicated data. And our statistical methods don't have to be complex, but we should be very careful about making sure that the statistical methods we're using are appropriate for the data that we're trying to draw inferences from. And also that we have these opportunities, right? These new technologies are giving us new chances to apply these statistical models in ways that we couldn't have done previously. And we actually learn a lot more by doing that, right? It's not that we want complexity for complexity's sake. It's that we need complexity because we're dealing with complex systems. And oftentimes we learn more when we sort of build models that are appropriate for the data sets that we do. So used to teaching, I feel like I should stop and ask if there's any questions. No. So going back to this idea of new technologies, I'm gonna highlight a couple of technologies in this talk that we're using in our lab quite a bit. Although I want to stress that, a lot of this is not specific to the technologies that I'm going to mention. They apply to, everything up here as well as other data sets that we could gather using that. So one technology that I want to talk about is this this collaborative network of automated telemetry stations that's been set up over the last decade or so called MODIS. This is a program run by the Canadian Wildlife Service. Each of the dots here is is a tower that looks something like this. So this is VHF technology. There's actually one of these towers over on building 4. If you've never seen one, and you get a view, you can see it from building 3. The idea here is that, anybody can set up one of these towers. We can then tag birds or bats or insects, a lot of different organisms with these specially coded VHF tags that are compatible with this network. The tags now are very small. They're as small as like 0.1 grams. So you can put them on butterflies and things. And then in theory, as you release this bird and it flies away, and if it comes, within a few kilometers maybe of one of these towers, it gets picked up and reported back to you. And there's a lot of excitement about this. If you go to any ornithological meeting, there'll be dozens of talks based on MODIS data. We can track birds using these small tags to learn about movement, to learn about demography, to learn about all sorts of things. But as I'll get to, it's complicated. This is an example, I'll talk about this in a little bit, of best case scenario, what MODIS data looks like. Each of these lines is an individual bird. Each point is the detection of that bird at one of these towers. And then we've sort of divided it up by winter, during spring migration, and then when the birds arrive back on the breeding grounds. So, this is cool. This is a lot of data that previously we had no way of collecting. Another technology I'm going to talk a bit about is RFID or pit tagging. If you have a pet that's chipped, right, it's the same technology. If you scan a Prox card to get into a building, same thing. We've been developing these bird feeders that allow us to track individual birds, right? So this is a bunting that's got a leg band on here that has a pit tag embedded in it. This is sort of our first generation feeder. You can tell how homemade they are. But basically it's a bird feeder. The perch is a little antenna hooked up to an RFID reader, powered by a solar panel. And then every time a bird lands on the feeder, we get a log of which bird it was, time, date, that sort of thing. So again, these feeders are very inexpensive. We can put them out in the field. We can collect this data, high resolution, relatively low cost, a lot of stuff we can do with it. This is some more RFID data that again, I'll talk about in just a minute. Each of these points is a bird that's these birds are being tracked over 3 years. And so you can see, over time, we get a bunch of detections, sometimes thousands of detections of these birds in a week or a couple of weeks. A lot of stuff we can do with this data. If you are a wildlife ecologist, or if you've taken any kind of wildlife ecology methods type class, both of those data sets may have kind of looked somewhat familiar to you, right? We can sort of conceptualize both of those data sets as, right, we catch a bird, give it some sort of mark. This bird got a purple polka dot hat. Every bird gets a different color hat, different pattern, something like that, right? So we can identify that bird, we release it, and then we hopefully encounter that bird again in the future, right? So here's, maybe this is a MODIS tower or a RFID feeder or a camera trap or an acoustic telemetry array or whatever our technology is. But we, detect that bird in the future. And again, this data looks pretty familiar, right? If you're a wildlife ecologist, and I say this both from my own experience and from seeing people analyze data like this, our instinct is to treat this like capture recapture, right? And so the way we sort of think about capture recapture data is we're gonna bin up our time, we're gonna choose some, maybe this is week or month or year, right? We bin up that time, and then we just keep track of, in each one of those time bins, did we detect the bird or not? If we're really fancy, maybe we have different states that the bird could be in, like breeding or migration. And so instead of just zeros or ones, we keep track of what state the bird was in. But again, these look pretty familiar. And as wildlife ecologists, we're pretty comfortable with data that look kind of like that, right? So what we do is we treat each one of those like a capture history or an encounter history. Looks like standard capture recapture data, so it's really tempting to put that data into an existing program that allows us to estimate survival or transition rates or whatever it is, using CJS model or multi-state model or something like that, right? And we've got these great programs that do that, right? We've got Program Mark and RMark, and you've taken a class where you have some code that does that for you. And so you fit this model and it spits out parameter estimates. It doesn't give you an error message. And so if you're a grad student, right, you're feeling pretty good. In my experience, both from doing this myself as well as listening to talks, reviewing papers, what often ends up happening is that the parameter estimates that are going to come out are not particularly realistic. Survival rates tend to be implausibly low. Movement rates tend to sort of contradict what we sort of know intuitively from observing our systems. And oftentimes, we're either left kind of scratching our heads about, well, that must be wrong, so what went wrong? Or we just try to plow ahead and say, these are our best estimates of, survival of this species, and it just is what it is. Oftentimes, if you dig a little bit deeper, what you realize is that the data that we collected is not capture recapture data. We just kind of shoehorned it into a format that made it look like capture recapture data and then put it in a model that we're familiar with. And what ends up happening, right, is that the model that you used has a bunch of assumptions. And when we take data and we kind of shoehorn it into this format, oftentimes we end up violating a lot of those assumptions. If you're a student, right, you've probably taken a stats class where you had to learn about the assumptions of a model and your professor kind of went on and on about it, right? Like if you're in experimental design, I know that applies to you. And hopefully you took time to learn those assumptions and understand what they are. But kind of looking at going to conferences and reviewing papers, I think people sometimes tend to either ignore or forget those assumptions. So I'm not going to spend a whole bunch of time on this, on the actual assumptions, right? If you fit a CJS model, these are the main assumptions, right? Hopefully if you fit these models, you know that. The point is, oftentimes the sort of key to using these new data is to think through how does this data set violate the assumptions of the model? And oftentimes these kind of new technologies do in unique ways. If we kind of go through the data sets that I just talked about kind of one by one, if we're assuming that all of our marked individuals are representative of the population of interest, there's a lot of reasons that may not be the case, right? What animals are we capturing? We can only oftentimes tag a subset of individuals based on their size or their health status. And oftentimes, despite our best efforts, we know that these tags can affect the parameters we're trying to estimate. Tags have effects on survival, movement, behavior, those types of things. All of these are violating this assumption in ways that could impact our inputs. Individuals within the same class have the same survival and detection probabilities during each time interval. Again, all sorts of ways this assumption can be violated, right? These are detections of painted buntings at MODIS stations. We know painted buntings go to the Bahamas. We know they go to Cuba. There's no towers there. We don't see them, right? So some individuals don't have the same detection probability because they're going to places where there's no towers or fewer towers. Even at a bird feeder, we know that there's kind of hierarchies and which birds use the feeder at any given time, and that can also result in heterogeneity in who it's detected in these feeders. Marks are not lost and they're recorded correctly. If we're putting metal leg bands on birds, this is usually a pretty reasonable assumption. These MODIS tags have these like very, very skinny metal, you probably can't even see it. There's this long antenna. Those break off. We're putting them on using these harnesses made out of fabric. Those harnesses fall off sometimes. These are really tiny tags that are pushing the limits of battery technology, and we're putting them out in the field in harsh conditions. Despite what the manufacturers tell us, the batteries probably don't last as long as we think they do. They fall off. If the tag falls off, our detection probability of that bird is no longer P, right? It's 0. The model doesn't know that. Also, despite what manufacturers tell us, there's problems with false positives in these data. This is some real MODIS data of a sharp-tailed grouse. I realize many of you are not ornithologists. This is the breeding range of sharp-tailed grouse, and they're not migratory. So either this grouse was doing something really weird, including briefly visiting Whitehall Forest, or these are a bunch of false positive data, right? This is obvious, right? We can pretty safely conclude that that sharp-tailed grouse wasn't in Athens. But if those detections were sort of within the normal range, oftentimes we don't really know that, and it can be harder to teach, right? Sampling occasions are instantaneous relative to time intervals. This is kind of a subtle point, but again, I just want to stress, right? Oftentimes, if we have two individuals, they each get detected once, we kind of bin up our time. Both of these individuals have the same capture history. In reality, this bird got detected at the very end of this time interval. This individual got detected at the beginning. This individual survived almost twice as long as this individual did by the time it got detected. But in our model, we treat those as if the probability of survival was the same. The degree to which this is a problem is sort of context specific, but it certainly can be an issue depending on how we treat time in the model, and that can cause problems. All immigration from the sampled area is permanent. Again, this can be violated in a lot of ways. Here's detections of individual birds at our bird feeders over 3 years. There's clearly periods of time where birds are not at the study site, but it's not a permanent movement away, right? These are migratory birds, so that in between seasons, they've left the study area. That's temporary immigration. Here's an individual that was detected really early in 1 year and then not seen again the rest of the year, and then it was seen again. It was somewhere during that time. Here's an individual that was present in year 1, not present in year 2, present again in year 3. Again, may not seem like a big issue, but those are complexities that can cause a lot of problems when we go to estimate things like survival. Come back to that point. Okay, that was very brief. I don't want to make it sound like those are specific problems to these types of data. Every assumption there's an example or oftentimes multiple examples in the literature of that assumption being violated by a specific type of data and modeling solutions to deal with that and to come up with robust inference. The issue is that oftentimes these new technologies are violating the assumptions in sort of unique combinations of ways. And oftentimes when people are eager to publish this paper with like, oh, cool, I estimated survival from MODIS data, maybe aren't always thinking through the unique attributes of MODIS data and how they sort of match the assumptions of the methods. The nice thing is, again, we live in this time where, I don't want to say complicated, but complex statistical methods are more accessible than ever, right? There is code and books and papers that can get you started on every one of these problems. And really the key is sort of developing a statistical toolkit that allows you to sort of match your analysis to the data. Okay, that's kind of that was a long intro. Now I'm going to go through some kind of specific examples and sort of walk through some real data sets where we've had to deal with these issues in ways that were both challenging, but also provided some cool new ecological insights. First one I'm going to talk about is estimating survival of alpine bird species using RFID. This is a project that kind of came with me from Utah. For those of you that are not ornithologists, in North America, we have 3 species in this group called rosy finches. They're alpine birds in the western United States. In Utah, 2 species are regular wintering birds, so gray crowned rosy finches and black rosy finches. Gray crowned rosy finches are sort of short distance migrants. They breed up here in the purple area. They come down to Utah for the winter. Black rosy finches sort of are these very high alpine specialists, but then in winter they come down to lower elevations. Both species are experiencing population declines. Black rosy finches in particular are a species of high conservation concern in Utah and a few other states because they're range restricted, they're climate change threatened. They're very difficult to study. We know almost nothing about these species in terms of demographic rates and movement. Partly because during the summer, they're up at these super high elevations on these rocky cliff faces where it's very hard to catch them and study them. And in the winter, they're very nomadic. So they sort of move around in these big flocks, and that makes traditional capture recapture really hard. There's been a lot of efforts to color band these birds and then recite them, but they color banded thousands of birds and recaptured like 3 of them total. So their sort of nomadic behavior makes them challenging to study. But they do use bird feeders throughout the winter. So we deployed these RFID feeders. We pit tagged both species of rosy finches with the primary goal of estimating annual survival. We don't know what annual survival is for this species. And then as I'll talk about, we kind of added these other objectives, not because we started with them, but because in order to estimate survival, we had to deal with these other complications. And in dealing with those, we ended up estimating some other cool things that were interesting to learn. This was kind of a fun project, especially if you're a winter weather person. The bird feeders were put up at ski resorts during the winter. Here's rosy finch using one of our RFID feeders. Over the course of 3 years, we pit tagged 320 gray crowned rosy finches, 68 black rosy finches. We had about 130,000 detections. So remember I said out of like thousands of color banded birds, there have been like 3 or 4 ever recaptured or recited. With these feeders, we had 130,000 detections of birds over 3 years. And we thought this was a really cool data set to try to estimate. We started off by treating this like capture recapture data and fitting a CJS model, right? So if you're not familiar, right, we're trying to track whether a bird is alive or dead. And we recognize that at any given point in time, we may observe it or not. And when we did this, we got super, super low survival. We realized that this probably wasn't going to work. And it wasn't going to work because there were all these complexities, right? We're trying to figure out if a bird is alive or not based on whether we see it or not, but whether we see it or not is actually a pretty complicated process, right? So now we have to have all these steps, right? So down here, we have, think of these as every day, whether we see the bird or not, right? So we saw the bird, didn't see it, saw it there. In order for us to see the bird on any given day, it needs to be using the bird feeder. That may seem kind of obvious, but these birds are nomadic, so sometimes they're just somewhere else and they're not using the feeder. We hypothesized that was very weather dependent. If they have access to seeds, natural seeds, they'll go eat the natural seeds. If it's really snowy, cold, terrible weather, they all use the bird feeder. So again, rosy finches are great if you like doing field work like in blizzard conditions, you'll catch lots of rosy finches. If you're from Georgia like me, it's challenging. Right, so if the bird is using the feeder, then we can detect it. If it's not using the feeder, then we can't detect it, right? So we have to keep track of that and we have to model. In order for a bird to use the feeder, it has to be present at the study site. Remember, these are migratory birds, so some of the year they're not there at all. So we can sort of think about, right, the bird is there and we can see it, it's there the next occasion. but it doesn't use the feeder, and then maybe it leaves to migrate back to its breeding grounds, right? So now we can't see it again. The second year, it doesn't come back to the study site at all, so we can't see it. This year, on this kind of first occasion, it hasn't arrived yet, then it arrives, then it's left. We have to keep track of that in order to accurately connect our observations to whether a bird is alive or not. And then these birds, again, are nomadic, so some years they might come back to the study site, some years they might go somewhere else. And so again, we kind of need to know on any given year, is the bird returning to the study site or not? So you can think of that as site. So this ends up being a pretty complicated model, but one that is necessary in order to get survival estimates. This is a little bit of data. I'll kind of go quickly through this because it's a little less important. Some of these parameters we assumed were kind of, it doesn't matter what species you are, it's all the same, you're just a rosy finch. Some of them are specific to gray crowned rosy finches, and then we sort of had a hunch that there were two groups of black rosy finches that use these feeders, some that are there all winter and some that we only see as they're passing through on migration. Some of birds, based on our observations, we knew if they were sort of winter residents or passage birds. Others we couldn't tell unambiguously, so we kind of let the model figure that out for us. And so we take all 130,000 capture histories, we put them in the model. Again, we wanted annual survival. This is kind of a cool model because we're keeping track of if they're there all winter and then if they come back the next year. So we can think of both overwinter survival. So these are overwinter survival probabilities for passage black rosy finches, migrant, wintering black rosy finches, gray crowned rosy finches. Survival between winters. So basically, your probability of surviving from one winter and then coming back the next winter, and then annual survival, which is the product of those two. So these are annual survival estimates, you know, somewhere in the 50 to 60, maybe 40 to 60% range. Again, that's pretty if you're not an ornithologist, that's pretty plausible for a 25 gram migratory songbird. And the first estimates of survival for this species, for either of these species at all. So pretty cool. Again, because we had to account for these sort of complicated movement behaviors, we got a lot of additional information, like the timing of arrival and departure from these wintering sites for each group. So these are, the thick line is kind of our mean estimate. On any given day of the winter, the probability that a bird either arrives to the wintering ground or in blue departs from the wintering ground. You can see for these passage migrants, right, they don't show up until late spring. They don't stay very long. They depart very quickly afterwards. The other two groups are arriving kind of mid-November through December and then departing in late May. So this is kind of cool information about their migration phenology and timing. We also got estimates of site fidelity. So in any given year, there's about a 75% chance that they come back to the site or not. And then we also got estimates of how these weather variables affect whether they use the feeders or not. And it kind of played out the way we expected it to be, that so this is probability of using a feeder. So as it gets really cold, their probability of using the feeder, there's a negative relationship. So as it gets colder, they're more likely to use the bird feeders. If there's a lot of snow on the ground or a lot of active snow, they're also more likely to use the bird feeders. So learn a little bit about their behavior during the winter and when they use it. Okay. Second example I want to talk about, and if you were at the first Warnell seminar with Dr. Cooper, some of this will be reviewed, but trying to estimate seasonal survival using automated telemetry. I mentioned MODIS earlier. Here's what kind of MODIS data looks like. These are detections of white-throated sparrows that we tagged at the botanical gardens, and then during spring migration, they get picked up at MODIS towers as they go back to their breeding grounds up in boreal forests. So there's been a lot of interest in using these data to try to estimate, for a lot of species, rosy finches notwithstanding, we kind of know annual survival pretty well. What we don't know for most species is when and where in the year mortality is most likely to occur. So are they dying during migration? Are they dying during the winter, during the breeding season? That's information that is lacking for most species. And so that's been a big interest of users of MODIS. The data set that I'm going to talk about, and again, if you were at the first seminar, Dr. Cooper already showed this graph, I think. He studies Kirtland's warblers. This is an endangered, recently removed from the endangered species list, migratory bird. They winter in the Bahamas, and they all breed in this little patch of Michigan right here. And Nathan spent a bunch of time tagging birds in the Bahamas during the winter. And then this little animation kind of shows them getting detected by MODIS towers during their spring migration on the way back up to breeding grounds. This is about as best case scenario as we get for what MODIS data can look like. This is the figure I showed earlier. This is all of those detections from that animation. So we get a lot of data during winter. We get some birds picked up while they're migrating back to the breeding grounds, and then we get some detections of them on the breeding grounds. And what we were interested in is estimating survival probabilities during winter, spring migration, and breeding to figure out when survival was lowest or mortality rates were highest. Again, the way we initially tried to do this was to just put it in sort of a multi-state capture-recapture framework. This can work. This paper just came out with sort of the multi-state version of this analysis, but it did have some problems associated with it. It's really inefficient. We got to loop over all these non-encounters. We also end up with these cases where there's some ambiguity, and within one of our time bins, the bird gets detected both during in its migratory route and during the breeding state, and you have to choose one of those or the other, which can cause bias and some ambiguity. So what we ended up doing is sort of thinking about, well, rather than treating this like capture-recapture data that's traditionally collected during these kind of discrete capture intervals, what if we just treat it like a continuous time event, which is what it really is. So what we're keeping track of now is the amount of time that passes between each detection and what state the bird was in during that detection. If you're familiar with multi-state models, you probably have seen something that kind of looks like this, where there's this matrix that governs transitions between our different states. In continuous time, instead of these entries being probabilities, they're rates. So the rate at which individuals die or transition to another state. Of course, we have to think about birds getting detected as well, but we can also put that in this model. So these become the rate at which individuals get detected if they're in the winter state, migratory state, breeding state. And then, this is what I don't want to focus on this equation. I just want to say this was really challenging, but it turns out, right, that you can formulate this model in a continuous time framework. You can figure out the likelihood of all of your detections, and then you can estimate this model sort of in the way that the data is observed instead of shoehorning it into something that's a little more out of the box. This was a huge headache. And so this paper is basically just my attempt to be like, nobody else needs to have this same headache. So if you want to do this. So this ended up working surprisingly well for Kirtland's warblers. These are the kind of transition probabilities. So again, thinking about migration phenology, we get estimates of kind of the probability that a bird is transitioning from winter to migration, so departing on spring migration, and then from migration to breeding, so arriving on the breeding ground. So we get these kind of estimates of the phenology of these movements. We also get hazard rates. This model is written in terms of hazard rates instead of survival probabilities. So high hazard equals low survival. And initially what we found, again, kind of what we expected, that hazard rates are really high during migration. Migration is very risky for these birds. So we were like, oh, cool, this works. And then one of my colleagues was like, well, what does that come out to in terms of annual survival probability? That was a good question, because when we sort of calculated annual survival, that That's like a 25% industry. Again, if you're not an ornithologist, that is an implausibly low survival probability for hikers. Which again, sort of pointed out like, okay, something is still wrong with this model. And after, some more head scratching and sort of banging our head up against the wall, what we realized is that this model makes an assumption that is probably violated with notice data. The assumption that it makes is that that detection process is more or less constant, given that you're in a certain state, right? So if this is kind of the detection rate and it's just the same at all times, you expect these detections at Motus towers to come at somewhat regular intervals, right? There's some randomness to that, but they should be somewhat evenly spaced. If you look at Motus data, this is sort of a made up example, but this is kind of what Motus data looks like, right? It's very clumped, right? If a bird gets detected once, it tends to get detected a few times and then a long period where it's not detected. In discrete time models, you might call this like a behavioral effect. This like looks a little bit like trap happiness, right? If you're trapped once, you get trapped again. In continuous time, it's a little bit harder. I have to give a hat tip to Richard, who I was scratching my head one day about what do you do? And he said, oh, have you seen these Hawks process models? And then that led down another rabbit hole. How do you do that? But there is a way to kind of deal with this in continuous time, which is basically you let that detection rate vary based on an individual's detection. So what ends up happening is if a bird gets detected, that detection rate jumps up. So now it's more likely to be detected again. And then there's this kind of decay function that gets detected. And that allows for this clumping. You thought I was joking when I said I was going to talk about self-exciting point process models. Wasn't joking. This is a self-exciting. So anyway, so after a lot of how do you code this, how do you do this, we sort of figured it out. Refit the model. And these are the hazard rates from the model that had that kind of Hawks process model detection. Still very high hazard during migration. So we still sort of ecologically are coming to the same conclusion that migration is very risky for these birds. But if you sort of do the calculation, this is annual survival of about 55%, which is pretty similar to what we see from color banding studies of these birds on the breeding grounds. So again, much stronger inference once we stop to think about what assumptions we were making and how our data violated assumptions. Okay. Wrap up real quick. A lot of this is for students. We study complicated systems, right? Ecological systems are just inherently complex. We observe those systems imperfectly, which adds additional complexity. Simple models are if you've taken experimental design, you've heard me say, if you can use a t-test for the data you have and the question you're trying to ask, use a t-test. Simple models are fine, but ignoring the complexity of both the ecological process that you're trying to model and the observation process that's generating that data doesn't make it go away, right? The complexity doesn't disappear just because you use a more simple model. Really what that comes down to is know the assumptions of your model and think carefully about how and whether you're violating those assumptions. And if you are, then that simple approach may not be one. All of these new technologies are giving us opportunities to answer questions that previously, 5 years ago, 10 years ago, we couldn't answer, right? We couldn't think about migration survival of Kirtland warblers even just 10 years ago. But those analysis of those data requires careful and deliberate analyses. The good thing is that quantitative training and quantitative tools are more accessible than ever, right? So if you're the type of person who sort of sees those equations and, gets a little intimidated or is just like, no, this is not why I got in this field, that's okay, right? But don't think that complexity is the same as just sort of statistical machismo, right? What we're trying to do is make sure that our analysis matches our data set appropriately. This is a little bit out of context, but I always love this quote from Mark Carey in one of his books. He's talking about this specific software program called JAGS, but really I think of the idea that as your statistical toolkit kind of gets bigger, it gives you the ability to not just sort of take out of the box models and shoehorn your data to fit it, but to actually kind of build models that fit the data and the questions that you have. That's why we make you take all these quantitative tests. I realize that I'm saying this as somebody who kind of enjoys this, and not everybody does, including our old friend Jimmy Buffett, who I think would disagree with me. The last thing I'll say is that Jimmy Buffett deserves to be criticized for this song, not because of what he's saying about math, but because it's a terrible song. Awful. But I don't think we should view Jimmy Buffett only through the lens of songs like this, because he also wrote songs like this, which are lyrical and vivid and storytelling. You also thought I was joking about talking about where you're With that, I'll thank these projects had tons of partners that helped with funding, data collection, analysis, all sorts of stuff. So many people to thank, and